Hi, I'm Muhammad Ali and today I'm going to discuss the CPU design and how it may be converted into HDL code. This is an example of its proposed CPU architecture design diagram that I'm going to use in develop and explain the CPU HDL code. The CPU in the diagram below is made up of multiple logic gates including ALU, A register, D register, PC and multiplexer. It will be easier to build the CPU HDL code in this unit because we have already built most of the logic gates from the previous task. Driving the CPU API is the initial step in implementing HDL code. The API specifies the chip name, input and output pins as well as the CPU function and other commands. The instruction memory and data memory are three input to the CPU that come from various sources in the computer. The M command and the reset are these inputs. The row, which is value of the specified instruction memory register, is the source of the instruction input. It is possible that this is instruction in either instruction or C instruction. In contrast, in M is the value presently the select data memory register, which the CPU utilizes to carry out its operation. The instruction memory and data memory are both related to CPU. The CPU receives instructions from the instruction memory and one of its input is the value of the specified data memory register. The reset input specifies whether we want to return the CPU its starting state or more precisely whether we want to reset the CPU function from the beginning. The CPU has various outputs that are connected to the instruction memory and the data memory. In addition to the input, write M, out M, address M, and PC or the program counter are the names of these inputs. Returning to the beginning, when we examine the CPU architecture, we can see the ALU produce a result that we return to the data memory. The ALU must define a few things in order to do so. First, the contents of the data memory that CPU will write. Second, the address of the write operation in the data memory placed in the out M. Essentially, this is where the material will store in the data memory. Finally, the output that allows CPU writes data memory return M with contents. The program counter stores the address of the next instructions, which is read, decoded and executed by the CPU in the following cycle. Now that we have established the CPU architecture inputs and outputs, we can start writing CPU code. The job resources included the HDL code from the CPU. As I progress through the presentation, I will go through each portion of the code in greater detail. The chip name as well as the name of the input and output pins make the part that specifies the CPU interface. Because this is CPU chip, the code chip name is CPU. The input pins of the CPU will be 16-bit data, 16-bit instruction and reset as illustrated in this code. 16-bit out M, write M, 15-bit address and 15-bit PC will be on the CPU upper pins. The CPU first section, there are three different gates in HDL code: NOT gate, gate and MUX 16K. These gates enable the CPU to function and carry out specified tasks. From the instruction memory, the CPU receives two short instructions. The A and C instructions are two types of instructions. The add value instruction has symbolic syntax. This value can be decimal, non-negative number or symbols. If A instruction value is a number, the instruction will change the content of the register to the value indicated in the instruction. If A instruction value is a symbol, the The instruction will set the contents of the A register to the value that the symbol points to, rather than the actual value in the memory register. The symbolic syntax of C register. The symbolic syntax of C instructions is thus equivalent to comp and jump. This instruction causes the CPU to do computation that is then stored in destination register or memory location. It can also command the CPU to go another instruction memory address indicated by the value or symbol in the first line. However, no gate is employed to determine if instruction arriving into the CPU from the instruction memory is an instruction. However, the CPU must first convert a 16-bit instruction into operation code and 15-bit value of. If the operation code is 0, the instruction is A. If the operation code is 1, the instruction is C. If the instruction from the instruction memory is an instruction, the CPU calculates 15-bit value and save into register. If the same structure, the A register can be supplied either instruction input or all output, and it will be perform the computations. The ALU output is supplied to the ALU and the A register output is fed to the ALU. The AND gate is used to determine whether the instruction on the ALU output is stored in the A register, and the 16-bit multiplexer is also utilized to pick whether the instructions or the ALU output is saved in the register. In the following section of the code, we have an OR gate loaded into the A disturb. If either the A instruction on the ALU output is supplied to A, the disturb will be 1. The A register, on the other hand, is used to store the value that given into it. As inputs, it accepts the output A register from the multiplexer and the output load A from the OR gate. The content or value currently held inside register is then generated by output A. Then there is an O16 that takes the output of the A register and the value currently selected in the data level register in M, and decided whether to output A or M. Depending on the structure value, either A or M will go into the ALU. The AND gate is used to decide if the ALU output is loaded into D register. Next, D register is then used to load and save D register value from the ALU. The ALU gate is the next stage, which completes the functions on 2 inputs. It consists of input control bits such as ZX, NX, ZY, NY, F, and NO, which indicate which function is computed on 2 inputs, produce output, and output control bits such as ZR, NG, which dictate the attribute of the result. The following code, which consists of 2 or 16 and AND gates, set the ALU output so that the data memory can be correctly returned to the address of the right operation is determined by the first O16 code line. The second one determines the data memory contents. Finally, AND gate output a value that allows the CPU write data to data memory. The PC program counter is registered the source address of the instructions to be fetched. The load bit of the PC is then decided by the jump bits and the ALU output in this section of the CPU. HDL call basically these lines of codes check the ALU output to see if the conditions are met and calculated jump conditions. If the instruction is C and criteria are met, the program counter is loaded with the value that instructs the CPU to jump to given value or symbol. PC is increased if the PC is not loaded. The CPU will read the next instruction after incrementing. So that's how I interpret and apply the HDL code for the hacked CPU. Thank you.